Without further delay, it's my pleasure to introduce Brent Theroux. He'll be presenting construction over deep compressible soils. So please join me in welcoming Brent.
Thank you, Miguel. All right, if I ever dwindle off and you can't hear me, just shout out, please speak louder. Thank you. Many thanks to the conference committee for inviting me to speak here. I'm very excited to be here. So excited, we're going to dive right in and hit the ground running. So I got a lot to show you. Hopefully we get through all of it. So I'm talking about the Twin Ports Interchange. It is essentially the topic of my talk is a large ground improvement system, how we investigated it, analyzed it, constructed it, and confirmed that it performed as it was intended. Some headlines and themes we're going to talk about: poor soil conditions, the analysis and the modeling that went into that analysis on which a design was based, and then the construction of that design using construction methods that weren't quite as well understood going into construction, and then a robust monitoring program throughout all of it to confirm that it was performing as expected. So I'll go through the kind of the standard outline. You're going to get some background. I'm going to talk about some soil conditions. I'm going to hit the analysis and the design, the construction, and the performance. And I'll tell you what these little things are in this picture. The Twin Ports Interchange. This is in lovely Duluth, Minnesota. You have to get used to that. This is in lovely Duluth, Minnesota. This is the old interchange. Lake Superior is on the right, Duluth in the background there. And you can see there's a lot of ramps and different alignments weaving together in one spot. This is Interstate 35 on its way from the Twin Cities into Duluth. That goes from the foreground into the background. Off to the left, winding its way up the hill, is US Highway 53 that goes to the Iron Range. And then off to the right, those ramps that go to the right side of your picture that is I-535 over the port into Superior, Wisconsin. So it's a cluster of a lot of major traffic coming into this one spot. And the site for the ground improvement, if you can see that little yellow sign kind of in the center of the picture, from there back, in the far back, where you see an overpass going over the road, that is the approximate limits of the ground improvement program that was built. So why? Well, everything that you saw from that yellow sign to that overpass was on bridges. Some of those bridges are low-profile bridges, like you see here, where there's a lot of pile bents that support those bridges with exposed pile. It's a costly maintenance and inspection effort by the DOT. They wanted to get away from that. Moreover, all the freight traffic that comes into the port that is offloaded from ships and wants to get onto trucks, they can't use that interchange. The geometry is such that the really big components that come through the port have to make their way through city streets. So another ambition of this project was to redo the geometry of the interchange so that it was more friendly to heavy industrial traffic. Something I'll say here, but I probably won't mention it again, is this was an alternative project delivery. So this wasn't your standard design, bid, build project delivery. This is what's known as construction manager, general contractor. My colleague Mike Hagerty is going to talk more about this, I believe. Later on, he's the person that swapped slots with me to accommodate some personal conflicts, so thank you, Mike. But this project was also, like his project, an alternative project delivery. All right, some site conditions. Generally speaking, and I use that term loosely because soil conditions changed every time you stepped a foot across the site. Generally speaking, we had a zone of upper soft clay, lacustrine sediments, soft alluvials, some organics, even some naughty industrial fill that might be in the ground. And then we had a zone of lower clay, also alluvial and lacustrine, a little bit stronger, but not all that much. And that's fine and good, but what really made this site problematic was the layer of dense sand that was in between them that could come and go. It was anywhere from 0 to 40 feet thick, and it was very dense. So if we look at something that's going to support high embankments, some retaining walls, some of those might be on, say, piles or other column elements, it's going to be hard to get that stuff through dense sand. But then sometimes if it's there, it's only 5 feet thick, we're going to plow right through it and not even know it. So that was a challenge on this project. And I got some boring logs here because I couldn't help myself. You can't read that, but it's soft. It's way to hammer, more compressible, more way to hammer. This is a cone sounding, which really illustrates how that dense sand, you can go from really soft weight to hammer material, and then your tip resistance in the middle of that plot shoots way up, and it's really, really dense sand. But then underneath it is more compressible material. And we even found some metal debris in peat, of all things, in spots where we hit metal debris. So, okay, that's bad. Moved over, drilled again, hit more metal debris, the same depth, moved over, hit it again. The running joke was there's a Volkswagen on this job somewhere. Who's going to be the one to find it? So we did what's known in the industry as a crap ton of borings. We did all those soil borings and CPT soundings, and we put all of that into a three-dimensional soil model, which you see at the top of the screen. So this is a continuous 3D model of all the subsurface conditions. And from that, we can cut a cross-section through there and get a look at, on a per-station basis, what do we think is going on in the subsurface. So in this cross-section, that green and brown blob to the right is our kind of floating dense sand layer. And you can see it exists to some thickness on one side of the alignment, but on the left side, it's gone. And then we can, from that, come up with some nice plots that show us, depth to the top of the sand and, what contours of thickness, perhaps. So it was very useful to try to get a handle on what are the bad soil conditions here. Okay, analysis. This was a column-supported embankment system, and if you're not familiar with that, it's an embankment supported on columns. So generally what it is, it makes really simple physical sense. You have the weight of an embankment that's going to be supported on columns, and you transfer that load by a stiff mat or platform. You can think of it as a really big glorified pile cap. If it's perfectly rigid, it will transfer those loads directly into the columns, but that gets to be a really large mat and platform if that's all heavy-duty reinforced concrete. So typically in these systems, what's built is a aggregate platform of well-graded, compacted aggregate interspersed with some geosynthetics to get it stiff, but it's not all that stiff. There is some give to it. And the mechanisms we look at when we design these things, we look at these three mechanisms. We're looking at settlement. That's the overall thing we're trying to treat and address. We don't want the roadway or other structures to settle. But you do get some settlement in between the columns. So you want to keep track of that and see what's the magnitude of that, how big a deal is that. Then we look at load transfer into the columns. Is the load arching between columns the way we expect it to? And then sometimes, if the settlement in between columns, if the soils are soft enough, and along the edges of these systems, if the grade is steep enough, say you have a wall, you can get a phenomenon that we call lateral spreading, where even that little bit of settlement in between columns is enough to sort of shove the soil out of the way. And to the outside of the system, there's nothing there to confine it. So it has a tendency to flow out and spread off to the side. And when we're building rigid structures like concrete retaining walls, or maybe we have some drainage infrastructure there, a little bit of movement could be a big deal. Some slides on the columns themselves. What do the columns mean? Well, they can be a lot of different things. In this case, rigid inclusions is the industry term for unreinforced concrete shafts that can be installed really quickly in soft soils, and we used a lot of those on this project. You could also use steel piles, and we did in fact use some H piles in some select areas. But you could use timber piles, you could use aggregate columns, whatever deep foundation element that you think suits your job, you can do that. The load transfer platform, like I said, it's a thickness of compacted aggregate with some geosynthetics layered in to help get it stiff. That's typical. You could do concrete, and in fact, we did have a small part of this job where we had to use a concrete load transfer platform, but it's very commonly compacted aggregate. Okay, this is a mock-up of the new interchange. It kind of looks like the old one just because there's a lot of wavy roads going everywhere. But now the distinction is, instead of everything supported on pile bents and typical structural foundations, these are supported on embankments, and they're faced by retaining walls. We've got MSE walls, we've got concrete walls on piles, and concrete walls on spread footings. And so when that happens, you've got rigid elements interacting with soft elements. And in the engineering analysis, when you have high modulus rigid walls and piles interacting with low modulus, soft soils, our conventional analog ways of evaluating that can be complicated, they can be tedious, and they can be overly conservative, sometimes really conservative. And so it's really been in the last several years where numerical modeling software has allowed engineers to look at the discrete interactions. And so we can, in a finite difference model or a finite element model, look at all of the different deformational interactions, elastic interactions between all the materials, and iterate that and can come up with a result that shows just what the displacements are. To do that analog with just equations is very challenging, if not impossible. So that's why we use what we'll show you next is a three-dimensional numerical analysis software. Also, something to point out on this slide. In the red, you're seeing the ground improvement columns is the focus of our analysis. In the blue on the left is a bridge abutment or a retaining wall supported on its own pile system. And the challenge on this job was that was going to get built first. So now when we go in and put all these columns in, how does just the very installation of those columns affect this bridge abutment that's not backfilled, that's only newly built? And in fact, we found there is an effect. You do have the possibility of moving that. So the question was, would it move too much? What if that was an existing bridge carrying live traffic during the first year of construction? How big a deal is that? So that was another focus of our analysis. To start, we did a very robust field test where we piled an embankment, supported it on a small footprint of columns, put again a crap ton of instruments in it, and measured just what the deformations in the ground were, what deformations beneath the embankment were, what the settlements were, just to get A, some proof of concept that the system would work, and then B, based on those results, we could calibrate our numerical models to match the behavior of the soils on site. And then C, get more of a firsthand look of, as these columns go in, how do they affect nearby infrastructure? Like this in the lower photo, there's bridges to the side that are carrying traffic. Are those at risk in any way? And I want to point out that my colleague at the DOT, Rich Lamb, wrote a paper on this and presented it at a conference a few years ago. So he's got all sorts of plots and results on that. So I'm not going to go through all those bullet points, but suffice to say, we built a large 3D numerical model at the center of the interchange that encompassed all of the different bridge abutments, retaining walls, reinforced zones for MSE walls, the different material sections, so for the load transfer platform, for working platforms, for general roadway fill, that's all incorporated into this model. It takes a long time to get the geometry created and set in the model, but once you do, you can start iterating on different parameters, tweak some of the interactions between different elements, and do a nice sensitivity analysis to see what are the critical areas of the project. And then also what's nice is we take that large 3D soil model we created from all of our soil investigation, and that gets directly imported into here and is spatially correct from one end of the model to the other. And then all of our columns go in there as discrete elements. So we don't make any generalization on any sets of columns or anything. We can isolate on any given column and see, is it performing the way it's supposed to? Is it in failure? Is it bending? The model allows us to do that. All right, I'm going to show you on the next two slides two cuts through the interchange along those two black lines. And the way we did our first run is we assumed that our columns, wherever that floating sand was 10 feet thick or more, we told the program in an algorithm to say our columns are going to go 2 feet into that, and that's where they'll bear. If it's less than 10 feet thick, then our columns are going to go through that and down to the till and bedrock at the bottom. So here's a result. Quick aside, so a partner on this project was Itasca Consulting Group, and my dear friend Augusto at Itasca did the modeling for this. I love Augusto dearly, but he is in love with the metric system, so all of the results come out as millimeters or meters, and I got to go in and benchmark that so you see 0 and 5 inches. So if I missed any spots, I apologize. I tried to catch those. But on this, that green and red zone over there represents a high fill. That's almost 30 feet of fill being placed over existing grade. And the red zone represents a zone of soil that is settling, and is settling as much as 5 inches. And the top of that zone is at the bottom of the embankment. So beneath our load transfer platform, we're seeing settlements of up to about 5 inches. At the top of that embankment, where it's shown green, we're seeing 2.5 or less. So that's one thing to look for in these systems is, yes, you will get settlement, but this is showing that you're not getting the magnitude of settlement in places you don't want it. So it's the road we care about. The road's not settling, and on this project, the tolerance for road settlement was 2 inches. This was tolerable for the design. If we look at a cross-section 90 degrees to that, we see that big red zone again. But again, the tops of the embankments shown as green are showing at settlement at acceptable levels. That red blob to the left side of it, that is that's a boundary effect. Yeah, that looks bad, doesn't it, Brent? But it represents an area where we have untreated ground. So it was, we couldn't quite scrub that from the model, but that was not an area that needed ground improvement treatment. Lateral deformations. We can look at the effect of lateral spreading. How much do the soil, the walls, especially at the toes of walls, how much are they spreading outward and kicking outward? We can analyze that, and this is showing that we saw lateral deformations of not quite 4 inches, more in the 3 to 3.5 inches, as predicted by the model. In reality, we saw much less than that. But it was still enough that in order to properly mitigate it, we put in a system of large diameter steel rebars in the embankment. So that was another feature of the ground improvement system. And these are slides showing just, again, we can look at individually the axial strain and stress within those bars to make sure that they're not yielding. We can look at individual columns, and this is just representing a case where we had columns where most of them were stopping on this shallow sand layer, but then we have a small subset that's, no, they're going right through it. And when you have a sudden disparity in column length, what does that do to the column performance? All right, so what does that look like as a design? So this is a typical section. We got high fills on the left and right, and then a low fill area in the middle, which would settle if not treated, but it's lower. We've got columns from one side to the other at different spacings from 8 to 10 feet apart. Load transfer platforms, 3 feet thick beneath the higher fills, only 2 feet thick beneath the lower fills. And then our layers of steel rebar in the embankment. This particular section had number 10 and number 14 rebar. And then one critical case we found through the analysis was in spaces, in parts where columns that were out in front of walls retaining high fills, those were at critical risk of failure and bending. So we had to put steel rebar cages in those columns to mitigate against bending failure. So there's a picture of the columns and a group of them that were exhumed. Concrete strength of the columns was specified as 5,000 PSI. Their minimum diameters is 16 inches, and they're installed as what's called full displacement columns. And I've got a slide that will better illustrate what exactly that means. For the high fill areas, termination criteria were to take those columns down to a hard bearing stratum, wherever the soil model says a hard bearing stratum was. For the low fill area, those columns were only up to 60 feet in length, and those were supporting the low fills in just frictional side resistance within the soft material. Oop. At the tops of the columns, as a way to optimize spacing, we had caps. So each column had a cap. For the high fill areas, we had 3-foot diameter caps. For the low fill area, it may sound counterintuitive on its face, but we needed bigger caps because of the thin height of the load transfer platform. The math works out that you need if you want to have columns farther apart, you need to mitigate that by having your edge-to-edge cap distance, make sure it fits and matches within just a 2-foot thick layer of LTP. And there's a picture of the steel cages that went into the columns. For the load transfer platform, on top is the conventional compacted aggregate load transfer platform with geogrid. On the lower left, there is the special concrete load transfer platform that we poured. And that was to span a new 72-inch storm sewer that was being placed inside a 96-inch casing. And it was just too far of a span for the conventional load transfer platform to be able to distribute the stresses. So we put in a 2-foot thick fiber reinforced concrete platform. This is a picture of the steel rebar. On the top picture, it's intermixed with the steel reinforcement of the MSC walls. But those serve to help, those work passively. So as the embankment may have this tendency to spread out due to that lateral spreading phenomenon, it will engage those plates, and then it's that passive engagement that prevents the embankment from spreading more. We also, that's harder to see, but we had one area where the limits of our improvement came up against an existing embankment, and in order to mitigate settlements that we thought would happen, we would have had to excavate a substantial part of that embankment. So instead of doing that, we had a lightweight fill area to mitigate those settlements. So we had some areas where geofoam was used as a transition from our column-supported part to a non-treated part. This is a picture of a temporary wrap face wall, again, that had to be explicitly addressed, make sure we had columns supporting that during the first year of construction. So it was just another one of those specific challenges that can happen on any project to make sure we addressed support of this wall during construction. Overhead signs and some of the tall light towers, those were also located throughout the footprint of this ground improvement. And sometimes those were supported just as spread footings within the fill over top of our improvement system. Other times the foundations were low enough we could directly and structurally connect the columns right into those footings. So the columns themselves, those were rigid inclusions is the conventional industry term now. On this project, we just call them columns. But that is showing a rig that augers down using that tool. And what happens is the flights on the edge of that tool dig into the ground, but the tooling diameter bulges out partway up from that, and that serves to push the soil to the side. So it's displacing the soil to the side, keeping it in the ground. This was selected because it was low spoil risk at the top. We didn't want spoil from the ground coming up to the surface for environmental reasons. So once it goes down there and pushes the soil to the side, there are ports at the end of the tooling which open up, and then as the tooling is withdrawn, the whole column is tremigrouted from the bottom up. The whole thing can take 5-6 minutes. It's very fast. Some of the longer columns may be closer to 10, because we did have some 100-foot columns, but it goes very fast. You can do over 100 columns in a day. We did load tests on those columns just to confirm the suitability of the bearing layer that they were bearing on, but then also as a way to check that the contractor's means and methods were consistent, that they supported the analysis that went into putting that column on that bearing layer. But the load tests themselves are not a great way to establish termination criteria. And that was a big challenge on this project. So contrast with pile driving, you can just count blows and you get a sense of how well that pile is engaging the soil at depth. Hey, are we getting the capacity we want? With columns, as of the time this was designed, there was no standardized way to specify what the termination criteria was. And indeed, different contractors have different ways that they collect data as they put a column in the ground. Some of the common things they track are things like torque, crowd pressure, grout volume, the rate of advance and withdrawal. But depending on the equipment, those can have different degrees of meeting. Some contractors will put a lot of stock in torque. When they see a spike in torque, hey, we know we're in something good. Other contractors, not so much. So that was a challenge on this project. The initial spec for the project gave a torque rate. It's kind of made up, but we needed something to give contractors to bid on. But then we explicitly said, hey, we know you're not going to like that rate, so we're going to do a series of demonstration columns at the beginning, and we will collectively come to an agreement on what constitutes termination criteria. And in this case, for this contractor, they had a dimensionless factor that their system spit out that we then calibrated to the needs of our design, and it worked out very well. There was a lot of angst in the beginning, but once we got that established, it was invaluable to set the termination criteria and then review logs for what amounted to thousands and thousands of columns. Thousands and thousands of columns. So we had 6,375 of those rigid inclusion concrete columns. On top of that, we had over 1,700 H-piles. The reasons we had H-piles, I don't have time to go into. In hindsight, we probably didn't need to use them, but it was a bit of a compromise with the DOT's bridge office. But those are counted as part of the system. So all told, we had over 8,100 of these elements going in the ground. And that encompassed a plan area of 13.8 acres. Okay, that's great. Did it work? Let's find out. So again, the things that we look at when we design these systems, we're looking at settlement, load transfer, and lateral spreading. Those are the kind of the engineering things. But then installation effects was this construction-based phenomena that we had to be sure that we kept track of. Was that going to be a big deal or not? Spoiler, it kind of was. So for instrumentation, to track settlement and lateral spreading, we used what we call shape arrays. I'm going to get yelled at for this by other geotechs, but they're kind of glorified inclinometers. They're automated. They can collect data up and down the length of the hose. And we put those in horizontally as a way to measure settlement. And so we put those underneath our load transfer platform. We put those in vertically to measure lateral deformations. In the columns themselves, we had strain gauges on steel cages in the columns as a way to measure the take-up of axial strain and stress in columns to make sure that the columns are accepting the load. We also had strain gauges on the lateral rebar and the embankment, and that was a way to look at lateral spreading. Are we getting take-up in those bars of axial strain, showing that they're resisting some tendency of the embankment to move to the sides? Qualitatively, we also put in vibrating wire piezometers. They're great for everything. We put in a lot of them. In this case, it helped us look at pore pressure increases in the soil, which might be an indication that the soil is going to consolidate, but it also is an indication of just how much those pressures spike due to installation when we put the columns in the ground. We also put earth pressure cells at different levels of the load transfer platform. I don't put much stock in the quantitative readings of earth pressure cells, but they're great for looking at relative increases or decreases in earth pressure. And so that was a qualitative redundant check on load transfer. And then we tried to put in some conventional settlement plates as a second way of measuring settlement. We tried. And that slide's just for in case anybody asks me how many of those things we put in, I can tell you. So those are all the geotechnical sensors. In addition, we put in structural monitoring devices to help us look at, again, the installation effect of all these columns, thousands and thousands of columns, hundreds of thousands of yards of concrete going in the ground. What is the cumulative effect on other stuff while that's happening? The red squares and polygons represent bridge foundations on piles that were installed prior to the ground improvement going in. That green rectangle represents live traffic on an adjacent bridge, old bridge. So this is all in close quarters. These columns are going in just feet away from these features. So we had tilt meters in those locations to look at vertical rotation. We had an automated total station with prisms that shot at intervals around the clock to look at different ways the structures might behave in three-dimensional space. They moving away, closer, left, right. And then on the far right, we did something that I think at the time was kind of novel. Maybe it's been done before. We put one of our shape arrays, again, that's this glorified inclinometer, inside the pipe pile that supports one of the bridge abutments. And the thought there is if the piles supporting those bridge abutments are going to want to feel that soil deformation against them and they're going to want to deform, hopefully we see that in this pile, and we'll see just how much of deformation does occur. All right, for settlement, I'm going to zoom in on this wall. It looks like a lot of the other walls, but this is actually the highest fill on the site. This is the same spot of the 5 inches of settlement slide I showed you earlier. This is just a picture of our shape array going in the ground. So that high fill, one side of it is an MSC wall, the other side of it is a cast-in-place wall supported on piles. This is the deformed shape of that sensor as it goes underneath the fill between the walls and then also to the left underneath the low fill. So you can see the deformed shape. Each line represents a snapshot in time. So it starts, the top line is at the beginning, and then as you place fill, it sinks and sinks and sinks and sinks. And as the lines get closer together, you're seeing less settlement per unit of time. And hopefully in the far future, all those lines are plotted on top of each other. This settlement shows about 5.5 inches of settlement. And Augusto's, my dear friend Augusto, the modeler, his estimate of settlement at this spot was 5 inches. I've never seen a modeler hit the nail on the head with a settlement prediction like that. We usually will over-predict settlement, hopefully. Hopefully we're not under-predicting settlement, but we hardly ever get it that close. So that's why I'm standing up straighter, straightening my tie. It's pretty cool. The 3 nodes, the next slide is going to show the displacement versus time at each of those 3 nodes. So you can see we get most of our initial settlement right away at the beginning on the left during fill placement, and then as time goes on to the right, that displacement levels off. We enter more the creep domain of the soil sediment behavior, and that levels off. We have more data to even beyond this slide, and it levels off even more. The settlement plates, man, we tried. I really wanted to have ways to show how the settlement below and above the LTP, how it was different. But we had challenges with getting baseline readings, getting readings when rod extensions were added, and so regrettably, I don't have great data on the settlement curves. What I can show you, though, is what's shown on the right. If you ignore the vertical axis, which can show that some of those series of plots have up to 10 inches of settlement, which is incorrect. But once grade was achieved, and we were no longer adding fill, no longer adding rod extensions to the settlement plates, we saw pretty flat behavior on the settlement plates. So it's not everything, it's better than nothing. That showed that once we achieved grade, we saw less than a ½ inch of settlement movement through the settlement plates. Load transfer. These are the strain gauges that we installed on the columns. So it's kind of a key. I show a column on the right, and each color on the plot corresponds to a level in the column. So the blue plot corresponds to the top of the column strain gauges. The brown is at the bottom. And where we saw the maximum load take up is the green, which is just a little bit off the bottom. So we do see the columns take up load and then kind of settle in to carrying a more consistent load throughout the column. This particular plot shows very well where the neutral plane would be. So if you're familiar with down drag, we're seeing that the neutral plane is right about where that green bar is on the column on the right. Earth pressure cells we used as more of a qualitative way to look at load transfer. So again, I have a key in the upper left showing where the color of the cell is in the load transfer platform. The blue is at the top of the load transfer platform between columns. The red is at the top on top of a column. And we see the most load going into those cells and not decreasing as much over time. The black one was at the bottom of the LTP between columns. That's where we would expect to see the least earth pressure acting on it, because we want to see load going to the columns. So for black, we see an increase in earth pressure at the beginning as they're building it, but that drops off as the system starts to interact with itself and load starts to get distributed to each of the columns. The load felt by that black earth pressure cell starts to decrease. Well, then why, Brent, is it increasing at the far right? Well, these are not systems where they accept the load and then it doesn't change. It will change. I mean, as one column accepts load over here, it might lessen over here, but then it has side effects to the other ones. So there's thousands of columns, and there'll be some feeling out of it as everything settles into place. So it's not unexpected that we see some variability on that, even after it had decreased. For those lateral bars, there was some feedback from some on the team is, do we really need those, Brent? This is showing that, yeah, those did take up a heck of a lot of strain to help prevent the embankment from spreading outwards. Would it have spread outwards a lot? Well, who knows, but it would have looked bad. I mean, the walls might crack, MSE panels would be out of place, maybe some storm sewers get jostled around and don't work as well. So this was necessary. What's notable on this one is the group of plots on top represents one side of the wall. That's one side of the embankment. That's the MSE wall side of the embankment. And the plots at the bottom, the blue and red, are the pile-supported cast-in-place wall on the other side. We expected this to be reversed. We thought that more axial strain would be seen by the portions of the bars next to the pile-supported wall. And that's because if everything gets built up and lifts, that MSE wall it's more permissive to deformation. And so it's going to move over there, and it's the far end of those bars that are going to be anchored into place and prevent that from moving more. The opposite happened. Why? Well, that's because the contractor decided we're going to build up the MSE side of everything first and not backfill behind the retaining wall. It's fine, it worked, but that's not how I would have expected it to go. Installation effects. So, again, just to reemphasize, that bridge on the left is carrying live traffic during the first year of construction, and we've got columns going in and within 10 feet of that, and we've got hundreds of those things along this stretch. And during the test embankment, we saw the ground shift 4 inches just by putting in a small group of columns. Now we're putting in 10 times that. So the piezometer there this is showing the increase in pore pressure as felt by a piezometer. So we do see a sharp spike in pore pressure over 10 feet of head, just due by putting columns into the ground. And then after the columns were in, we see another slight bump just from fill placement. But what really excited us, I guess, was the encased SAA that we put in the piles that were supporting the bridge footing. So on the right, you see a corner of a bridge footing. In between those cones is the stick-up of one of our sensors coming up out of the pile. So on the left, you see the bridge abutment on the left side, and then 2 rigs installing columns on right next to it, to the right of it. And the plots on the right, the blue dashed line represents the straight sensor inside the pile. That's the baseline. And then there's an animation running. I hope you can see it. Every half a day, that line moves, and you can see at about 30 feet depth, it bulges outward over 2 inches as the columns go by. So you can see it bulge coming in and out as they're making their passes, installing in the columns next to the abutment. That pile bulged over 2 inches just due to the columns going in. And what's more, if you look at the top of that animated curve, that's the actual footing. That's the top of the sensor as it protrudes through the footing. So the top of that footing was shoved over 1 inch laterally just from those columns going in. This bridge abutment was the highest abutment on the job, and it was one that's going to receive those sweeping curved beams for some of the large passes. An inch out of tolerance at the top of that abutment was a big deal to some of the bridge designers. I don't know the whole story, but I was told there was some things that had to be done to make sure that the top of the abutment had to be corrected in order to receive the beams. In the end, they were able to do it, but it wasn't like, oh, it's no big deal. It still worked. No, there were some adjustments that needed to be made. So when I give this talk and I illustrate this side, it's the bridge structural engineers that get really wide eyes and like, whoa, never would have thought that happened. Yeah. Yeah, so the pile itself was a 20-inch diameter pipe pile, so not small. There's certainly bigger ones out there, but it's not a small pile. Okay, I got some more comments. How am I doing on time? Good? All right. All right, just some of the weird quirks that came up during the job. I touched on this already, but abrupt changes in subsurface conditions. We have our 3D soil model, and it's great and all, but still on the job, we could have a column go down 40 feet, struggle to get another foot into whatever material it's in, presumably that dense sand. Okay, that's great. And then we go 8 feet over to the next column, and it goes down 90 feet. That happened often. So there were times where we had to go back to the model, rerun an analysis assuming different column lengths just to make sure that the design was still adequate for those changing conditions. Existing foundations, that was another challenge. So that previous interchange, there were pile vents everywhere. Those piles got cut off in the ground. Some of the substructures were actual column foundations with a footing and a pile cap. Sometimes those pile caps were removed, other times they were not. And I was told, Brent, for the ones that are not removed, you're just going to have to deal with it and put your ground improvement around it. And that's great, but then later I was told, no, those actually did come out. And so keeping track of that during construction, making sure we are putting extra columns in the ground if we need to. And then in some way, there's a little bit of anxiety around, I'm going to rely on a foundation pile cap that's been there 60-some years as an integral part of our system. It turned out to work, but at the beginning, there was a little bit of trust that needed to be built there. Challenges with grouting those rigid inclusions. That's one of the challenges that contractors will tell you is you put all these columns into the ground and it's all liquid, wet grout each time you do it. There is risk of communication between adjacent columns. So if the soils are really soft or if you've got water-bearing lenses in between them, sometimes that grout will shoot through those lenses and you'll see it come up in the column next to you. So we don't like that. On this project, we didn't see a lot of it, but we did see one peculiar scenario where this is a plan sheet. Those are all columns. The yellow boxes are columns where it was reported to me, we've got grouting problems. We're either seeing communication from an adjacent column or we're seeing grout loss in a column. It's going somewhere. The green ones were ones that were fine. I looked at this and thought, man, if I didn't know any better, I'd say there's a pipe in the ground. No, Brent, there's no pipe. There's no pipe. Until somebody says, Brent, I think there might be a pipe in the ground. The yellow is a 42-inch reinforced concrete pipe that I was told would be taken out. That's why we have columns through there. Well, when we plot where that's supposed to be, it's right in line with those yellow columns. So this is a quality control measure for construction. They got paid to take out the pipe, but they didn't take out the pipe. So I don't know what happened to the contractor after that, but hopefully there was some payment adjustment there. All right, I'll blow through these. Settlement plate. Oh, these poor settlement plates. So I like settlement plates a lot. They're really cheap. When done right, they work. But if you don't do them right, you're setting yourself up for a lot of headache and anxiety down the road if you're going to rely on the data collected from those settlement plates. So that's just one soapbox of mine that I've started to get on the last couple of years. If we're going to use them, you got to make sure we take the diligence to do it right. that happened to be a very angry day. That's not an accident. That's somebody mad at me, I think. All right, so I just regurgitation some other concepts I already stated, but that's the interchange as it looks today in the winter. It's open to traffic, everything's open, so worked out very well. Acknowledging all members of the team. This was a project that, I mean, one might think every consultant in Minnesota was a part of it at one point or another, but the DOT, the Ames Kramer contracting team, the roadway design team of SEH, that led by SEH, bridge design team led by Parsons, and then the ground improvement team, which was Barr, Itasca, and Stonebrook. So, thank you. You don't have to ask questions, that's okay.
What was the timeline, I guess, from the start of the investigation to, let's say, through this, like, great with that?
MnDOT did start a preliminary investigation, I think even before 2015. The design time, once it went into, hey, here, we're starting design, that was 2018. We got brought on board when design was about 15% complete, and that was late 2018 or 2019, can't remember. There was a couple years in the middle of there where things just went weird. Construction ended in 23, most of the major construction. I think there were some elements in 24 that were done, but everything was open in 23. Yeah.
Ongoing monitoring, are you still tied to that, or is MnDOT taking over?
MnDOT took ownership of the whole monitoring system. At a certain point, nothing was changing, and so they decommissioned it. So that was done about half a year ago, I think. Yeah.
So along from the inclinometers and the improvements and stuff that data that you guys collected, how long did it take for that to be out?
Good question. It was a few months, I want to say. I should go to it to be sure, but so once it starts to flatten out, that's fall of 22, and then the far end of it is January of 23, I think. So it gives you some idea. Thank you.